Okay, so hello and welcome back. So in this video I want to say a few words about the resonant frequency and the experiments that we had in the previous videos, and then we will move on to some circuits involving resonant frequency. So basically what we said about the resonant frequency was that if you had some sort of a circuit, the circuit that we talked about in the previous videos was basically you had an inductor, and then you had a capacitor over here, and then that capacitor was connected to a resistor to the ground, and then this was your V of out, this was your V of in, and this is your L, C, and R. Okay, and we were monitoring the voltage across this resistor, and the graph of the voltage versus frequency of this circuit was something like this. If this is V of out, and if this is F of in, the output was actually something like this, and this point is basically, and this peak basically happened at F of R at F of R, which is called the resonant frequency. Now about this resonant frequency, a few words. So basically basically the resonant frequency is the frequency at which basically the reactance of your inductor and the reactance of your capacitor are equal, meaning that X of L is equal to X of C. And then in the previous video we did some algebra on this, meaning that X of L is equal to 2 pi Fl, that is equal to 1 over 2 pi Fc, and then in this equation we solved for F, and we got F, and we called it F of R is equal to 1 over 2 pi the square root of Lc. So that's the frequency at which the reactance of your inductor is equal to the reactance of your capacitor, and we called it F of R, or resonant frequency. So it turns out at this resonant frequency, the reactance, at this resonant frequency, the net reactance of the inductor of this inductor and this capacitor is at minimum. Okay, and then what happens is that since the net reactance is at minimum, that means that the voltage drop across these two will be at a minimum, and so the voltage drop across your resistor is going to be at the maximum, and that's basically why this thing happens over here, that you will get a peak in your voltage at this frequency. Okay, so now why basically the net reactance of these two at this frequency is at the minimum? That's something that has everything to do with the physics behind these circuits, and we will deal with that more in physics. Not here is not the right place to talk about that. We will talk extensively about that in physics, or probably in some other electronics related courses that we will most probably do in future, but well, not here. The videos that we are doing currently right here at least with this playlist is more geared towards hands-on electronics, because we want to actually be building things with these videos, but of course we are not done with the theory yet. Once we are done with the theory, we want to actually work with these, work with the theory that we have learned here. It's not about, it's not going to be mainly about theory, but the theory is required for us to understand a thing or two about AC circuits, resonance circuits, filters, and things like that, and transistors and things like that, and then we'll be able to use that in different circuits in order to basically design analog circuits and things like that. We will have some theory courses in the future, and in those theory courses we will mainly get to the physics parts behind electronics, and then we will talk about those, which is going to be probably, I don't know, at least a year from now, or 6, 7, 8 months from now. Not very soon, but we will do that. Okay, so that's basically all about resonant frequency. Now the same circuit that we have here, and this is basically an RCL circuit. So the same circuit that we have here, we can actually use it in a different configuration and use it as a something called a notch filter. So basically a notch filter is basically some filter whose output is actually something like this, exactly the opposite of the output of this, exactly the opposite of this output, meaning that it's going to be something like this, and this is going to be your resonant frequency. This is F of in, and this is V of out. So at this frequency you will have the minimum amount of voltage across your output, and then that's basically the exact opposite of what we had before. And the circuit is basically, it has the same components, and a resistor, a capacitor, and an inductor, but in a slightly different configuration, meaning that you have to use the resistor first, meaning that the resistor is used in order to the incoming signal comes into your resistor, and then you have your capacitor here. You have your capacitor here and your inductor there. Okay, your inductor there, and your inductor goes to ground, and then this becomes your V of out, meaning that so this is your R, this is your C, this is your L, and as you can see, your V of out, you are measuring your output voltage across both the capacitor and the inductor. Okay, and it makes sense that this circuit would have an output like this, because in the case of this circuit, we said that at resonant frequency, the inductor and the capacitor will have a minimum, net minimum reactance, and so the voltage drop across them is going to be at the minimum. The voltage drop across the resistor will therefore be at the maximum, and then we got this peak over here, and so the same kind of thing happens here, meaning that at here again the same thing is happening, meaning that at resonant frequency, these two, the capacitor and the inductor, will have the minimum amount of reactance, and with minimum amount of reactance, most of your voltage is going to be dropped across this resistor. There is little voltage drop across these two, and so as a result your voltage is going to be at a minimum at resonant frequency, F of R. So that's basically, and this thing is also called a band reject filter. Also a band reject filter. A band reject filter. Okay. So it's called either a band reject filter or a notch filter. So now I have put together a circuit here, but I had some difficulties with this circuit last night, and I will take care of those problems now. We will get to the rest of the. I think there is something wrong with. It's supposed to be clean, and then let's see. Okay, so basically before we do the experiment, the same experiment here using, I have already prepared the circuit, but this circuit was actually behaving in a little bit differently than I actually expected. And let's calculate the resonant frequency for this circuit and then do the experiment again. Maybe last night I made a mistake or something in my calculation. So this thing over here, this is actually an inductor, a very small inductor. This is a capacitor and this is a resistor, and I've connected them together in the exact same way that I have drawn this circuit. Okay, so, and I want to basically test that notch filter or band reject filter. So, but before we do the experiment, because we want to know basically, because we know that this dip is going to happen at resonant frequency, we need to know what the resonant frequency for this circuit is, so that we can expect where to play with the function generator. So for that purpose, I'm going to calculate the resonant frequency for this circuit. And what I'm going to do is that basically the value of my capacitance here is 0.01 microfarad, and then now I'm not really sure about what I'm saying right now, but I think that my L is equal to 10 microhenry, and my resistor is 990 ohm. Now if that's the case, the resonant frequency, or F of R, is going to be equal to 1 over 2 pi the square root of LC, which is basically 0.01 microfarad into 10 raised to power negative 6 farad times L, which is 10 microhenry. So 10 into 10 raised to power negative 6 Henry. So that's equal to basically, this is 10 raised to power negative 2, and this is 10 raised to power negative 12, so that's 10 raised to power negative 14. So that's raised, and you have a 10 over here, so that you would get 10 raised to power negative 13. 10 raised to the power negative 13. 10 raised to the power negative 13. Okay. Don't want to make mistakes here. I'll calculate this. So this is a 10 raised to the power negative 2. 10 raised to the power negative 2 times 10 raised to the power negative 6 times 10 times 10 raised to the power negative 6. negative 12, negative 14, negative 13, which is this thing over here. Okay, so now if I calculate 2 pi times the square root of 10 raised to the power negative 13 and take the reciprocal of that, that's going to give me 503 kilohertz, which is what I got last night as well. 503 kilohertz. But what I noticed last night was that the output was actually at the minimum at about 10 kilohertz or so. Maybe, I don't know, maybe this inductor, the value is kind of different than what I'm basically calculating in this over here or something like that. But let's do the experiment again. Let's see what we get. Okay, so I'm going to use bring the camera over here. So I'm going to use this okay, so I'm going to use the signal generator that we have there, this one. And right now, then I'm going to use this counter and this oscilloscope here. And okay, so let's say that you have, and this is the output from the signal generator that comes down here. So I connect the signal generator to the circuit, and you see, based on the circuit diagram that I have, your input goes into the resistor, and then your ground becomes the inductor. So that is your ground. Okay, I use the channel 1 on the oscilloscope to monitor my input. And so this is my ground again, and channel 2 for the output. And the output is basically where you want to basically measure the voltage across both the capacitor and the inductor, meaning that both the capacitor and inductor. So this is going to be my output here. And then this becomes my ground, and you can see that of course the frequency is way too low, about 10 Hertz or so, but the input and output are kind of the same thing. And then if I increase my frequency, I go to the beginning of the range and multiply by 10, increase the frequency, to about 10 times, I don't know, 100 Hertz. So you see the output input are still kind of the same, 30 volts, 30 volts. And then I go to the beginning of the range and then multiply by 10. So again, I get the same 100 Hertz. So again, I basically start increasing the frequency. I'm not, the output is not dropping or anything. And now I'm at about 1 kilohertz. So go to the beginning of the range and multiply by 10 and start increasing the frequency. And now you can see that right here it's starting to decrease, that the output is starting to decrease at about 3 kilohertz or so. And at 10 kilohertz I'm at here about, I don't know, about 20 volts, 24 volts or so. And if I go to the beginning of the range and multiply by 10, if I increase the frequency here, you see right now I'm at about 40, 45 kilohertz. The output is way too low. It's about 5 volts or so. What the hell is that? Okay, so it's about 0.8 volts or so. 0.8 volts or so. That's actually 10 volts. So it's about, I'm sorry, 8 volts or so. And so now I'm. It's on 5 volts, so 5, and basically that's 1.4, so 1.4 times 5 is equal to 7 volts or so. Okay, so okay, so now I'm at about 7 volts. If I increase the frequency again a little bit, now I'm at about 100 kilohertz. It seems that's about 100 kilohertz. Oh, I got past the resonant frequency actually. It was 50. No. That's 503 kilohertz. That's about 500 kilohertz. Okay, so right now I'm at about 100 kilohertz or so. And you see the output is at about 4 volts. Is about 0.8, so about 4 volts or so. And if I go to the beginning of the range and multiply by 10, increase the frequency, you see that your output is now the frequency is 360 kilohertz. I think the 500 kilohertz frequency, resonant frequency, kind of makes sense. Let's see if that actually does make sense. So at 360 kilohertz, my output is at something about basically 800 millivolts. And right here, this is $525. Okay, so that's actually what the calculation also told us. Okay, so and then if you get above, so let me go to 503 kilohertz. Although this 500, so it's right over here. 533. It's telling me it's 533. It's right this frequency, which is I'm at the lowest point of my voltage, and then if I increase even a little bit more, you see that the output is actually growing again. Okay, and if I go to the beginning of the range and multiply by 10, you see that I'm at 900 kilohertz, and then you see the output is still increasing and increasing, and but it doesn't get, it gets to, at 4 megahertz it gets to about 2.2 times 5 is equal to 11 volts, but my output is about 10 volts right now. I'm sorry, 20 volts. So I get to about 11 volts, and then if I increase the frequency a little bit more, the output still again starts to come down to basically, and that's the end of the range that I can go. That's 10 megahertz or so. So it's kind of, it's like a polynomial, not exactly the, I mean, the curve that we saw on the output of the circuit is actually correct, but there has to be basically more curves. I mean, the curve must actually have more curves at different frequencies all the way down to the range if you keep increasing your frequency. So so now in the next, I'm going to basically go way down in frequency. Okay, about 10 hertz or so, and this is my input output. And now I'm going to do this I'm going to do this experiment again. Now the way that I'm going to do it, I'm going to actually note down some values and see what we can do with the data. So okay, so now let's I will put this circuit over here, and I will basically get some data from this experiment. So I have my V of in, I have my basically frequency, I have my V of in, and I have my V of out. Okay, and then what we have here is basically right now I'm at about 8 hertz or so, and you see that of course I cannot read much right now, so I go over to the beginning of the range and multiply by 10, and right now I'm at about 40 hertz or so, or even 10 hertz or so. So at 10 hertz, that's where we can actually start to see something, and this is my output. This wave over here is my input, this wave over here is my output, and see, both of them are set to 10 volts basically per division. So you have 1, 2, so that's about 30 volts per division. To be more exact, it is basically 1 to 2.8. That's 28 volts peak to peak, and my output is at 28 volts peak to peak. Okay, volts peak to peak, volts peak to peak. So that's 28 volts peak to peak, and that's 28 volts peak to peak, and the frequency is about 10 hertz or so. So that's in hertz. Okay. So now if I basically go over to, for example, if I go all the way up to 100 hertz, my output is about 29 volts peak to peak, and here I have about 29 volts peak to peak. So at 100 hertz, it's 29 volts peak to peak. I go to the beginning of the range and then multiply by 10 and start increasing the signal, and you can see that not much is happening in terms of the magnitude, and right now I'm at about 1 kilohertz or so. So at basically 1 kilohertz, the output is again the same, so 29 and 29. I go to the beginning of the range and multiply by 10 and start increasing the signal, increasing the frequency, and you see that my input output are kind of the same, but right here at about 3 kilohertz or so it starts to fall. So at about 3 kilohertz my input output are the same, 29 volts and 29 volts, and then at for example 5 kilohertz or so, at for example 6 kilohertz or so, my output is at about 2.6, 2.7, so that's 27 volts, for example. That's at 6 kilohertz. And at 10 kilohertz, I'm at about 2.4, so 24 kilohertz. 24 volts. That's at 10 kilohertz or so. And I go back in range and then multiply by 10 and keep basically increasing the frequency, and over here you see that at about 24 kilohertz my output is at about 2.5, so 2.5, 25 volt. What? I'm sorry, 1.1, it's about 15 volts. So at 24 kilohertz or so, 24.8 kilohertz, my output is at about 15 volts, or peak to peak. And right now I'm at about 43.6 kilohertz. My output is at about 10 volts peak to peak. Okay, at about I have to And right now I'm at about 100. Let me see what happens at about okay. So at about 100 kilohertz, my output is at about 5 volts peak to peak. 102 kilohertz basically. 102 kilohertz. My output is at about, so my input has jumped down to 28 volts, and my output is basically at 5 volts. I go back in range and multiply by 10 and start increasing the frequency, and at this frequency, which is 218, something like 218, the output is at about 2 volts peak to peak. So that's 216.6 kilohertz. The output is at about 2 volts peak to peak. At, for example, somewhere about 415.2 kilohertz, 28 volts. This is about 500 millivolts peak to peak, 0.5 volts peak to peak. And at at 510, exactly at this frequency, 527 or so, you see over here, I'm decreasing them at 407 kilohertz, and it's set to 0.2 volts, basically vertical. Okay, if I keep increasing, you see I'm increasing. I get to this point, and then it starts reverting back and increasing in magnitude. So at this point, somewhere over here, my output is about, of course it's not really fun to have this sort of output over here, but my output is at about, it's not a sine wave anymore or anything like that, but it's at about 1.30. So 1.3 times 0.1 is 0.13. 0.13 at, and now the frequency, you need to calculate it here, because that's the point where actually your output is at the minimum, but I don't want to read my frequency at this point from on this counter, because it's off by probably a few tens of kilohertz or so. So I come back over here, and if you come over here and take a look at 1, 2, 3, 3.24, 5.557, 3.57 horizontal units times 0.5 microseconds. 0.5 microseconds. It's equal to 1.785 into 10 raised to the power negative 6 seconds, and if you take the reciprocal of that, you get 560 kilohertz. And here I'm reading 549 kilohertz. Let me read again. So let me write this down. 560 kilohertz. So you see over here I have, if I position this here, I can't, unfortunately I can't read on this thing unless I come down here, and then I'll be not actually not a good way to do that. So let's go back here. Let's go back here and go back here, and we can read the frequency over here. So it's basically 1, 2, 3, 3.5, 3.55, I would say. 3.55 into 0.5 microsecond, and if I take the reciprocal of that, I get 563 kilohertz or so. Okay, and that's basically where you have the lowest amount of output over here. And if I increase my frequency, you will see that the output starts to rise again, and it starts to rise. So at 930 kilohertz, I'm at about, at 930 kilohertz, I'm still at 28, and over there I'm at about, so that's 2.4 times 0.5 times 0.5 is equal to 6/5 of a volt, which is 1.2 volts. 1.2 volts. So if I go back in range and multiply by a 10, so now you can see that if I increase my signal, and you saw that in that whole range, basically my output was kind of distorted. But right now my output is coming back to shape, coming back to something like a sine wave or so. So right now I'm at about 1.6 megahertz or so, and my output is at about 2.4 times 1 is 2.4 volts. 2.4 volts, 28, about 28, and the frequency is 1.6 megahertz. And if I go back, we keep going in this direction, something about 2.3 megahertz or so, or 2.7 megahertz. My output is at 2.6, 2.7. So 2.7 times 2 is equal to 2.7 times 2 is equal to 5.4 volts. 28, and that's 2.7 megahertz. And then you can keep going in this direction at, for example, 3.7, at 3.8, 3.9. Your output is at about 10 volts peak to peak. 3.9 megahertz. But my input has also a little bit changed, meaning that my input is at 10 volts now. So I have kind of the full output there. So I basically my output is at 10 volts. My output is at 10 volts. My input is at 20 volts, right? So I have half of my input at the output. That means that I could kind of think of that as 14 volts on this from meaning half of 28 volts would be something like half of 14 volts. I don't really know if that would actually happen if I had, for example, 28 volts on my input, but for now I just take it to be so. And then if I keep going keep increasing my signal, you can see that I have my output is at about 20 volts. My input is at about 10 volts or so. It keeps decreasing. So there was a point where the output was actually changed direction, and that was basically this point over here. Meaning that right now my input is about 20 volts. My output is about 12 volts, and if I go back a little bit, we are increasing here, and this is the peak. This is the peak, and right now I'm at about 1.05 times 0.2 microseconds. 1.05 times 0.2 microseconds, which is equal to, take the reciprocal of that, it's 4.76, no, sorry, 4.76 megahertz. At this frequency, my input is at, let's take the input as it is, it's at 20 volts peak to peak, and the previous output I want to take it as it was, so I take it as 20 volts and 10 volts. I don't want to mess with the data. Okay, so at 4.76 megahertz, the input is at 20 volts peak to peak. The output is at 2.2, so 2.2 times 10. 2.2 times 10 is equal to 11 volts peak to peak. 11 volts peak to peak, and that's the peak. And now if I, from this point, if I keep going, you see that my output is actually decreasing. So for example, at about somewhere about 6 megahertz or so, my output has come down to 1.4 times 5, 7 volts, for example. This is 5.9 megahertz. I have kind of the same, well, the input has changed to basically 1.8, so that's 18 volts, and my output is about 5 volts, so that's 1.4 times 5 is equal to 7 volts peak to peak. And then if I keep increasing the frequency, you see the output is actually decreasing, meaning that at 7.4 megahertz or so, my input is at about 1.5, so 1.5 times 10 to the 15 volts peak to peak. My output is at about so that's 1.9 times 2 is equal to 19 by 5, 3.8 volts. And then at somewhere about, I don't know if you can still see anything, but at somewhere about my input is right now at 123, so 2.8 times 5 is about 14 volts, and my output is at so let's see what that is. 2.2 times 1 is 2.2 volts peak to peak, and the frequency is 9.4 megahertz. And I can still keep going at, for example, 10 megahertz, 10.1 megahertz. I have, that's 2.8 times 5 again, which is equal to 14. My output is at about 1.9 times 1 is 1.9 volts. So 1.9, and this is 14 volts, and that's 10.1 volts, 10.1 megahertz. Okay, so that's basically all that I have. I can't go anywhere above 10 megahertz because that's basically the limit of my signal generator or function generator. But now something else that we can do as well is take a look at the phase shift on this circuit. And you want to go, basically we had 3 phases over here where the input voltage was decreasing all the way up to 563 kilohertz. From 563 kilohertz all the way to 4.7 megahertz, the voltage was increasing all the way to 11 volts, and then from there the voltage was still decreasing. So we can go between these three phases and see how the signal is actually, what the signal is doing. So I go down to somewhere over here, and as you can see, the frequency is somewhere about 100 hertz or so. So, and there is actually no phase shift here. So we have no phase shift there. If I go to the beginning of the range and multiply by 10, you see that still I have no phase shift there. Okay, go to the beginning of the range, multiply by 10, and still I have no phase shift there. I do have some phase shift here. The phase shift actually started here at somewhere about 7 kilohertz or so. Okay, so let me go back, see where the phase shift actually started. Okay, so right here I have no phase shift, right? And right now I'm at about 500 hertz, so still no phase shift. I'm increasing the frequency, and right over here the phase shift starts at about 2 kilohertz or so. So the phase shift starts there, and you see that the input is actually leading. Okay, so let me mix. Okay. Starts at about 3 kilohertz. Input leading. So the input is leading. Okay, and I want to go a little bit more to be able to read the phase shift. So I increase the frequency a little bit. And you can see the phase shift here. So if I go back in range, multiply by 10, now you can see the phase shift, and you can see the phase shift there. So you can go over here if you want to read the phase shift. So this is my output and this is my input. Now on this thing over here, basically the so if I were to read the phase shift over here, it wouldn't be that easy, meaning that you would have to basically, I cannot see the peaks over here. The peaks I don't really know where to, if I'm supposed to take it there or a little bit to the right or to the left, so I have to go back in speed, meaning that, for example, right now I'm on 5 microseconds the time base, so I go to 10 microseconds. Okay, so at 10 microseconds I can kind of see the peaks here. This is about the right place to be. And then you want to basically move both of your signals down here, but before doing that you need to find out what sort of, basically about the angles here. And to find out about the angles, so what you can do, you need to do a little bit of calculation, meaning that you see that you can move this around a little bit horizontally to for example set this trough to, for example, you can set this trough to this line over here. Okay, and then this is one complete cycle over here on your input. I'm not concerned about my output right now. So this is one complete cycle on the input, and that's happening in 2.4 horizontal units. So one complete cycle is happening in 2.4 horizontal units. So meaning that half a cycle is happening in 1.2 horizontal units. So that means that 1.2 horizontal units corresponds to 180 degrees. Okay, corresponds to 180 degrees. So now you can read the phase difference between the two signals, meaning that I can move this up here, and I would say that, for example, and you can basically move both of them down here to be able to read something that makes sense on this line over here. And then you can see that basically the phase difference over here is about 0.2, 0.4, 0.43 horizontal units. So 0.43 horizontal units, then 0.43 horizontal units corresponds to how many angles, to what sort of angle. So basically the calculation that I do is basically simple proportions. What I'm saying is that based on the input wave, we established that 1.2 horizontal units corresponded to 180 degrees. So then now the phase difference is 0.43 horizontal units, and we want to know what sort of angle that corresponds to. So then you can solve this proportion, 0.43 times 180 divided by 1.2, and that's 64.5 degrees. 64.5 degrees. 64.5 degrees. And of course you want to read the frequency for your phase shift as well, meaning that you go up here, the frequency of your input is this thing over here, and now I can of course change my time base a little bit to be able to read a little bit better. And this is the middle of this trough over here. Here is the middle of the trough, so that's 1 2 3 4 4 1 2 3 4 1 2 3 4 4.9, right? So 4.9 horizontal units times 5 microseconds. 4.9 horizontal units times 5 microseconds. And if I take the reciprocal of that, I get 40.8 kilohertz at 40.8 kilohertz or so. Okay, so that's basically my frequency. Now I think that this phase shift is not going to change, meaning that it's going to be, I mean, the input is going to remain leading at least all the way up to 563 kilohertz, which is where the output starts to rise again. Okay, so let me go over here, and now this is my output, and you see that the input is still of course bleeding. So now I want to increase my frequency, and I don't care if the angle changes or so, but what I'm concerned about is if the input stays basically leading, and it's still leading and you have no problem there. So I go down the range and multiply by 10 and start to basically increase my frequency, and I'm at about 460 kilohertz. So I don't really see the peak of this signal anymore. I move it down here. I think the peak is somewhere over here, I would say so. But you don't see the peak anymore. Okay, so that doesn't matter. Right now I'm at about 525, and I suspect that the input is still leading. So I go, and now you can see that the input is actually now and now you can see that right here at this point at 502, at 503, now the input starts to lag. Okay, and it starts to lag, and you can just keep going, but it's not possible to read any sort of phase angle based on the signal that you have here. So I keep increasing the signal here, and go to the beginning of, so basically it kind of happened at, the phase shift kind of happened at somewhere up about 507 kilohertz or so, which is about, so this is about, so now the phase angle is kind of at this point is cancelled out, and at this point it starts to basically now the output is leading, right? So when the output is leading, so what you can see here is that, so basically right now we are at this point where the output starts to increase, and now the output starts to lead. Right here the output was decreasing and the output was actually lagging. So there is a difference, there is a relationship between leading and lagging, and increasing and decreasing in magnitude, right? So leading increasing at about, so the phase shift is about, so the phase shift changes at about 556 kilohertz. The output starts to lead, okay, and then you can just keep going and see what's happening to your signal. And I want to get to some point where I can actually read something on this signal. So I go back in and I want to go somewhere. So at about 1.5 megahertz or so, the output is still, of course, leading, and now you can read some phase angles over here. Now you can read some phase angles, although it's not very, I mean, the wave, your signal is not that great, but you can actually read some phase angles here. So now the frequency is at basically 2.5 times 0.2 times 0.2 microseconds, 2.5 times 0.2 microseconds, and take the reciprocal of that, it's 2 megahertz. At 2 megahertz, okay, at 2 megahertz, let's read the angles here. So basically one complete cycle happens in 2.5, so half of that would be 1.25. So 1.25 is 180 degrees. And so then basically the phase difference here is what? Is basically, let's move this over here, let's move this over here, and let's move everything a little bit to the, so 0.2, 0.4, 0.6. So the phase difference is somewhere about 0.6. 0.6. So 0.6 horizontal unit corresponds to what angle? And now you can multiply 0.6 times 180 degrees divided by 1.25, and you'll get 86.4 degrees. 86.4 degrees. So now the output is actually leading. Output is leading by 86.4 degrees. Okay, And now you can just keep going in this direction in frequency, and I think that the phase angle is going to change, meaning that right now the output is actually leading, so the output will start to lag after somewhere about 4.7 megahertz, where the voltage starts to fall again. Okay, so I just keep going, and you see the phase angle doesn't change here, and I'm going to, still hasn't changed, and you see at this frequency, which is about 4.7 megahertz, there is almost no phase shift there. Both of the sequences are at the same, basically horizontally, basically kind of lined up. Okay, and at this frequency, you see the output is now lagging, and the input is now leading. And now when the output is lagging, it's actually decreasing. Okay, so you see over here what happens at this frequency. At this frequency, I don't want to measure much here, but you can see that at the phase shift changes again. At about 4.7 megahertz. So now the output starts to lag. Starts to lag, and the output VFPP, peak to peak voltage, starts to basically decrease. So I hope that you have gotten all the relationship between leading, lagging, and decreasing and increasing in the peak to peak voltage of your input output signal. So that's basically all of this experiment as far as the input output with peak to peak voltage and the phase angle are concerned. We will, in the next video, we will basically do a simple graph of this whole thing happening, and then do some calculations and analyze the data that we have a little bit. So see you in the next video. Thank you.